2212 Lab 5 Magnetic Molasses. The purpose of this lab is to demonstrate the effect of a magnet falling through a tube of aluminum foil, collect data on the magnet, model it computationally, and compare expected versus observed values. A brief preview of the results shows that the experimental time for the magnet to fall was 1.64 seconds, while the computed time was 1.42 seconds. Some of the principles used in this lab include the magnetic field of a dipole, Faraday and Lenz's law, Ohm's law, and the magnetic field of a current loop. These formulas are found in the reference sheet. For the models, the experimental tube had a length of 0.4 meters, an inner radius of 0.17 meters, and an outer radius of 0.21 meters. The magnetic dipole of the magnet was 2.66 ammeters squared, which was derived from Lab 3. The mass of the magnet was 0.025 kilograms. The magnetic fields of the magnet were determined with the phone magnetometer app, and the simulation was done with GlowScript. The average time for the magnet to fall through the tube was 1.64 seconds over 5 trials. For the first checkpoint questions, a ferrous tube cannot be used due to iron's intrinsic magnetism, which affects the magnetic flux and therefore the induced magnetic field inside the tube. The magnet falls slower due to the magnetic force induced by the current in the roll of the foil, and that is the physical principle behind this lab. In this code, the formulas for magnetic flux were used to analytically determine the magnetic field induced by the foil as the magnet is falling through the tube. From these formulas, a velocity versus time graph of the magnet as it falls through the tube was determined using the plot functions. The red currents in the velocity graph shows that initially gravity dominates and so the magnet accelerates, and then the velocity of the magnetic field induced by the tube opposes the force of gravity and makes the acceleration zero. Once the magnet falls outside of the tube, the magnet once again begins to accelerate due to gravitational acceleration. The red currents in the tube are counterclockwise. This is known from Lenz's law, since a counterclockwise current induces a magnetic field pointing upwards, slowing down the magnet, which has its magnetic dipole pointing down. If the magnet is flipped, the magnet will still fall slowly through the tube, but the current will flow in the opposite direction. The total time in the tube of the experiment is slower than in theory. Decreasing the time step and increasing the number of rings calculated will increase the accuracy of the answer. And reviewing the graph again, gravity is initially dominant, and then it is cancelled out by the magnetic force until the magnetic force falls out, and then gravity once again begins to accelerate the magnet downwards. Both the experimental and computational model generated the same type of forces, fields, and went the same direction. The magnetic force stopped the gravitational acceleration as the magnet continued to fall in the tube. The models differ since the computational model had no outside factors influencing the magnet, while the real-life model did. The computational model also assumed the magnet was dropped perfectly straight. Potential sources of error in this lab include other magnetic or electric fields interfering with the system, the magnets not being dropped perfectly, and the aluminum foil being loose and not densely packed. For the extension questions, as the resistivity of the conductor approaches zero, the magnetic field induced will be greater and greater, until it will be so great it exactly equals the gravitational force and cancels out. This is how superconductors work. If there were holes or slots in the tube, the magnet will fall faster due to less current being able to travel across the tube at those sections, since the current loops would be incomplete. Thank you.